已解锁，请取出话筒。
Okay, as a warm up, how about we do this question again? Yesterday we didn't do this question, right? You can use the usual continuous fraction to find expansion, or you can use this theorem to help you. Okay, yeah, use any of them. And let's spend 5 minutes to calculate for this question here. 1 plus square root 11 over 3. 开始啊，开始啊。Yeah. So I found that sometimes when calculating this thing, very frustrating. Although it's very repetitive, it's very easy to get mistake, and you don't know where to find a mistake sometimes. So so you need to be really careful when you do it. If you have answer to check, then that's very good. But usually we don't have answer to check. Okay, so let's see how it goes. Okay, so yesterday, someone mentioned that this is not satisfying the theorem condition because you don't have Q0 divide P square minus P naught. Good? Yeah, okay. But then we realize that there's a trick we can play here, right? We could transform this to 3 plus 3 square root 11 over 9 so that 9 will divide uh, 3 times 11 minus 3. Is it? We meant here yesterday. Did I get the sign wrong? D minus P square. Okay, sorry about that. D minus P square. So I put a square at the wrong place. So here will become 99 minus 3 squared, which is 90. Okay. Okay. So yesterday, I go back and test it. So I test the formula with this form and this form. Okay, I tested. So if I check the A0 term is the same no matter how you scale it. Okay, should be 1. How do I found 1? I use this argument here. I squeeze 11 between two perfect square, and then this perfect square, so it's squeezed between 3 and 4, and then I can squeeze this term in between 1 and 2. Okay, so this 1 and 2 is very important. You cannot say I squeeze in between, let's say 1 and 3, and then you argue that 1 is the greatest. It's not possible, right? Who knows this is greater than 2 again, right? But then now I prove that this is squeezed below 2. So that's why the greatest is 1. Okay, greatest integer is 1. And so that's why you need to really squeeze it with n and n plus 1. You can argue that n is the largest integer that less than the other. So you cannot squeeze too many room for this number to move around. Okay. Well, what I meant is this. So you need to be able to squeeze your number in between n and n plus 1. Okay. If you squeeze it in between n plus 2, then your number could appear on the other side. Then the largest integer less than the number could be n plus 1, not n. Does it make sense? Okay. So you could do this if you don't have calculator in your hand. Okay. So then you apply the formula. I think everyone should be okay with applying the formula. Okay. But then if you apply the formula with the original term here, okay, with the original term here, you also get the same number, but then the terms you get is not integer. Okay, obviously you can how to say you can move your denominator up. Yeah, sure. Okay, but then this is the final form of the formula. Okay, it's not integer, but they get to the same number. Okay. It should, right? It should, right? Because if you remember, I give you this idea here. There's nothing about divisibility here. Okay? There's nothing about divisibility. So I just do it the usual calculation. No divisibility. So the divisibility here happens to make sure that your number is always an integer. And so when you move to Q1, Q2, Q3, Q4, Q5, right? All these should be integer again. Okay, so if you look at this calculation here, if you look at this calculation on the left, yeah, on the left, right, it will always stand as integer. Understand? Okay, if you don't do this, if you don't follow this condition here, then your calculation will come out as a fraction. Okay, remember in this class, we always deal with integer, not really fraction. Okay, even we do continued fraction, right? That continued fraction, if you realize, is a fixed form. It's something plus 1 over something plus 1 over something plus 1 over something. It's a fixed form. It's not random rational number. So that we fix that form, and then we can relate rational number or irrational number to a string of integer again. Okay, if you notice in this class, we always deal with integer. Does that make sense? Okay. So again, you can continue play the same game. Did anyone manage to finish the calculation? I think I start again. Okay, I use the ChatGPT or Gemini to check answer already. Maybe I tell you the answer first, but seems like I got stuck again. So that answer should be 1, 2, 3, 1, and then repeat. Okay, so let me tell you where I stuck. So I got the 1 already. Okay, 1 is very easy. 2, I got it. And then 3, I got it as well. I got 1 as well, but then it should repeat. But then what? But then this term here is 1. If 1, 2, 3, 1, right, I should get back the same 1. So after I get this 1, right, I should get back the same where that I get this one so that I can keep continue this pattern. Okay, anyway, but anyone finish or where which term you finish calculate? Any term? No? Huh? Should be at least one. Huh? Which AI you stop? So just now we like give you 5 minutes. So which A you stop? Huh? Hi, Tiffany. Which term you managed to calculate? 啊，还没有啊，不用算嘛，你算到哪里？还在算一哈？没有，哎，这个一不用算啊，这个一。This one right? This one should be obvious from the term you started with. This term here. Okay, there's no like nothing you need to change. You just need to figure out this number is squeezed between 1 and 2. Okay. Then after the A0 turn A1, okay, you should use formula already. Okay, A1 you should use formula. Yeah, either you use this or you use the original formula. Yeah, anyone got A1? Can I see hand? Anyone got A1 here? Oh, A2 eh? Not yet. Okay. A2 anyone got? People only got A2. Oh, got A2? You got A2? Yeah. A3, you got A3? Did you get A3? A3, you also got it? Wait, let me check. Did you get this term for A3? Is it the same term? Same term? A3, you got it. A0, A1, A2, A3. How about A4? You got A4? Did you get A4? I want to check my A4 is correct or not. A4 is 1. So your alpha 4, is it this one? Same. And did you get alpha 5? Is a circle? Is a circle? Is a circle. But then alpha 5, what do you get for this one? Something wrong with my calculation. This is not divisible. I mean, like, 9 doesn't divide. Where's your alpha 5? Did you get your alpha 5? Hmm? What's your alpha 5? Anyone got alpha 5? You got it? Sorry? Alpha 4 is not? Is 9 wrong? 3? Denominator is 3? Oh, good. Thank you very much. Thank you very much. No wonder I feel so weird. Okay, so this one still hold, right? So it is 1. Okay, good. So now it's 99. So here is 3, right? And then here is 3 squared. Is it? Wait, let me check. What's the formula? So here is 2 square. Okay, divide by 3. Let's check this. 2. Here is 4. So 99 minus 4 is 95. There's something wrong again. 4. Not divisible again. Something is wrong again. How about A5? What do you get for alpha first? Alpha 4 is okay. Alpha 4 already repeat? Okay, let's check. Good, good, good. Okay, good, good, good. Okay, good. Alpha 4 already repeat. But then I should get alpha 1 right for the next calculation. Why am I not getting alpha 1? Wait, okay, so this is equals to alpha 1, good. But then if I continue, I should get alpha 2, right? Why am I not getting alpha 2? Let's see. 8 plus square root 11. No, no, no. I should get alpha 1. So this is alpha 0. Okay. So this is alpha 0. If I continue, I should get alpha 1 back, right? 6 plus 3 square root 1. So I should get 6 plus 3 square root 11. 7. Oh, also not quite right. Yes. So yeah,
1 times 9
1 times 9.
little multiply 3 before because it was 99.
Okay, 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 okay. Thank you, thank you, thank you. Yeah. Okay, so I missed out, isn't? Okay. So if I'm gonna use 99, okay. So if I'm gonna use 99, I need to use this one. This is what you mean. Wait, let me see. But then is this what I do before that? Okay, okay, okay. Okay. Yeah, okay. So this is a very important point, huh? Yeah, very important point here. When you pick your P4, Q4, right? Make sure this square root D, right, stay as the D you started with. Yeah, because after I simplify, right, then this is not the square root D anymore. This is like you already remove 9 from your D. Okay, so make sure when you apply this formula inductively, right, keep your square root D the same. Does it make sense? Yeah, yeah, yeah. Okay, so in this formula, what you should take is 3. Okay, so in this formula, I should take 1 times 9 minus 3 over 99 minus 6 square. 6 square, right? Because 9 minus 3. And then over 10. So over 9 in this case. This sound better. 9. Yeah, good. Okay. So here I get 6. Here I should get 7. So I really get back my alpha 1. Yeah, good. Okay, good. Okay. Yeah. Is it okay? Yeah, so be careful when you apply this formula, right? Where's this formula, right? Make sure that you keep the same square root D when you pick up your PK and the QK. Okay? Because sometimes it can get simplified. So be careful. So if you start with square root 99, then you have to do square root 90. Does it make sense? Okay, you can't change your d halfway. Otherwise, it doesn't work out. Okay. Okay. Any question on continued fraction? Any question on continued fraction? No? Okay. Yeah, so this formula is just a way for this kind of specific alpha you can use. And otherwise, you just use the usual method to find it, which is 1 over alpha I minus its floor. Okay, just use that. Because why we want to use the alpha method, let me show you why we tell you the alpha method. Because if I don't use the alpha method, then you need to write this long stuff, very long, you know? So you need to keep inverting, 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 inverting. Okay. If you have the alpha way to help you to work out, you just write down line by line is enough. You see? Can you see? Okay. The two things is the same. It's just that the way we record it, okay, is more efficient. Okay. Otherwise, you need to keep writing this redundant stuff here. Okay. It's the same thing. Just that you don't need to write so many 1 over 1 over 1 over 1. Does it make sense? Okay. It's a way of writing. Yeah, but if you feel that this way you know better, then you could use this, but you waste some times on this one if you write like this. Okay, so you can see that if I calculate like 4 terms, 1, 2, 3, 4, 5, 6, like you need 6 might be for the spaces, 6 pages. But then if you just write line by line, maybe you can. You see, this one we compute for like also 4 terms, right? We just need 1, 2, 3, 3 pages. Okay. Yeah, it's because the way of writing is different. It's the same thing, it's just the way of writing. Okay. You could use this if you feel more comfortable, but when the question get long, then you need a lot of space. Okay, yeah. Any more question on the continued fraction? Okay. Confident? Huh? Yeah. Okay. Okay. All right. Maybe we could try more exercise later. I guess maybe we could finish lecture 7 today. Hey, hello. Yeah. Maybe we could finish lecture 7 today. In that case, maybe we could have 2 days of revision lecture. If we have to, what? Do you want to revise 2 days or what? You like? Okay, you like. Okay. I thought we can cancel one. Okay, it's okay. If we have, let's say we have 2 revision lecture, right? Then we have like about 1 hour each for every chapter to do the revision question, lecture notes, and not the tutorial. Yeah, we could spend like 1 hour also for each chapters. Do you think okay? Okay. Okay. Okay, I'm doing this. Yeah, we also can discuss your assignment 4 if you like. Yeah, we can do together. Okay. So lectures 13. So we finally see this guy here, Fermat-Last theorem. I mentioned to you last time when we talked about Fermat-the theorem. So Fermat-Last theorem is kind of famous. Famous in the sense that there's a short story about it. That is, Fermat found a proof, but he says that this margin is too small for it to contain the proof. So Fermat went on and go and water his flower. Yeah, because Fermat is not a mathematician, by the way. Fermat is a judge. You know a judge? Huh? A judge. Yeah. So he do mathematics as his hobby. So what he does was he'll take a problem set and then work on it other than he going to the court. If it's not in the court, at home, he will do maths. That's it. Okay, this is Fermat's life. So what Fermat's last theorem says to us, if you increase the power of x, n, y, and z, n, there's no solution when this power here, when it is integer of n greater or equal to 3. And so Pythagorean triple is kind of a miracle, actually. Yeah. Who is that? Who is that? I don't know. Yeah. So this troubles the mathematician. 500, 300, 350 years. Okay. They have an estimate 350 years. Huh? Yeah, so there's a history on it on this story here, how people tackle this problem. But I think I want to mention one guy in particular. I want to mention this guy here. Okay, Gerd Fountains. Okay, so this Gerd Fountains here managed to show that s to the n plus y to the n equals zn can have finitely many solution in non-zero integer for a fixed positive integer n greater or equal to 3. Okay, so it managed to reduce the solution set to finitely many. Then if you show that this finitely many, all of them have to be 0, then Fermat last theorem is finished. Okay, obviously 0 will solve it, right? But then we want to see whether there's a non-trivial solution. Okay. Why I mentioned this guy? Because this guy just got the Abel Prize this year. Yeah, it's just announced last week, I think. Yeah, this guy got Abel's Prize. Yeah, Abel Prize is one of the mathematics prize other than few medals. Yeah. So this girl is very famous on this. Okay. Yeah, so this is about Fermat's last theorem. Actually, who solved it? Actually, it's this guy, Andrew Wiles. This guy is very special. He worked in solitary. What does it mean? He worked alone. He don't tell people secretly. Yeah, seriously. Then he after 3 years, 7 years actually. After 7 years, I think he kind of worked with his students actually. Okay. After 7 years, he come up and present the proof. Okay, present the proof. But then they found out there's a slight mistake. Okay, he go back and work with his student again together. And then I think after 1 year, they managed to solve it. And do well. Okay. Cool. So this is about that. So how to solve it? You asked why, right? Just now. It's not he asked why. Yeah. So the way they solve it is using geometry. Okay? It's not number theory. Yeah, they use geometry. They relate this equation here to a curve. You know that you can relate equation to curve, right? This is what you learn in calculus, right? You can draw the linear graph, quadratic graph, right, parabola, and so on and so forth. Okay, so this higher equation, higher dimensional equation will like sketch out surfaces, for example. For example, you also see surfaces actually when you go to calculus 2. Yeah. So they will have more exotic geometry associated to this equation. Okay, so let's continue. Okay, although we can't prove for all, right? Maybe we can prove for some special one that we can understand. Shall we do this? Huh? You think yes? No. This proof is kind of long for this one. But then I think we can prove some corollary. Yeah. Okay. So instead of proving s to the 4, y to the 4 equals to z to the 4 directly, right? One could solve this first. Okay, say that this doesn't have solution. This proof is quite long, but not too hard, I think. But I don't want to do in this class. Okay, but then let's say we know this. Okay, if we know this, can you argue that, can you prove that? This one is what I want you to think about. If I know x to the 4 plus y to the 4 equals z to the square has no solution, can you infer that x to the 4 plus y to the 4 equals z to the 4 has no solution as well? How are you thinking about this? Okay, so meaning you want to write this, okay, in the form that you already know there's no solution. Hmm. Mhm. Yes. Okay, so let me write down. So if you have any solution, so I try to use contrapositive or contradiction. So let's say this guy have a solution. Okay, this guy has a solution. What does it mean? This is also a solution for this kind of equation. You understand? Then it will be equals to some equation that you know that there's no non-zero. So there's a contradiction. Any solution to this form will be a solution to that form. Any solution to this would be solution to x to the 4 plus y to the 4 equals to w square, where w equals to x square. Okay. It will be a solution to some form that you know that there's no solution. So you cannot happen. So you prove one of the Fermat's last cases, okay, by this. Okay, obviously, this one is harder to prove. Lah. Okay, so you need to prove this first. Not, yeah, not too hard. Okay, so far, so good. For question? Question? Okay. So next. So next is about sums of squares. So we try to split our integer into sums of squares. Okay. Yeah. Previously you use prime factorization, right? Now we use sum of square. So now for 1 to 20, okay, try to write n as the sum of two square. Maybe I give you some examples and then you will try the rest. Okay. So for example, let me see. So we could include 0, I guess. Yeah, the squares here could be 0. So for example, 1 could be written as 0 square plus 1 square. And then 2 is 1 square plus 1 square. And 3 cannot. Okay. No matter how you, I mean, like the perfect square that's less than 3 is just 1 or 0. So you cannot use 0 or 1 to build up 3. Okay, so this is not sum of 2 square. Okay, but 4 is because you can add a 0 to it. Okay. Yeah. How about you try the rest until 20? Hmm. Okay, let's see. Okay, so 5. Okay, 5 can be written as 1 square plus 2 square. Okay, 6 and 7 are not 6, 7. Not sum of 2 square. 8 is 2 square plus 2 square. 9 is a perfect square, so automatically it is, because we are allowing 0 square here. Sometimes we don't allow, so be careful. See what people say. 10 is 3 square plus 1 square. And 11, 12 are not. 13 is 3 square plus 2 square. 14, 15 are not. 16 is 4 square plus 0 square. 17 is 4 square plus 1 square. 18 is 3 square plus 3 square. 19 is not. And then 20 is 2 square plus 4 square. Okay? So far? Okay. Okay. So let's continue. So there's a theorem here. If your number can be written as a sum of 2 square, then it cannot be 3 mod 4. Okay, so this is one of the criteria you check on. If it is not if it is not 3 mod 4, it could be a sum of 2 square. If it is, then it definitely not sum of 2 square. So meaning, what does this mean? You already throw away 1/4 of your number. You know, you already throw 1/4 of your number away. Okay, that cannot be written as a sum of two square. Okay, yes. Okay, how to prove this? This proof is very simple. Okay, this proof is very simple. So basically, you only started with two kinds of numbers, right? Even number or odd number. Okay. So if n is even, then n is like 2 times k or some k z. Then what's your n square? Sorry, I shouldn't care about n square, right? Wait, no, that's not what I meant. So mm, if n, okay, so I shouldn't write n here. Let's say I use a lah. Okay, if a is even, then a could be written as 2k. Then a square is what? A square is just 4k square. Okay, so if you consider mod 4, this guy is just 0. Okay. So let's say if b is odd, if b is odd, then b is equals to 2k plus 1. No, let's say use another terms here, maybe 2m plus 1 or some m in z. Then b square would be 4m squared plus 4m plus 1, which is 1 mod 4. Okay, so if it is sum of two squares, right, what will happen? Either 0 plus 0, 0 plus 1, 1 plus 0, or 1 plus 1. So you only get 0, 1, and 2. So you never get 3 or 4. Okay, so this is what how we prove it. Okay, so then a square plus b square is either 0, 1, 2, mod 4. Okay, hence n cannot be 3 mod. Maybe we started with suppose n equals to a square plus b square. Can we do that? Without loss of generality, should we without? Let me think. No, I shouldn't write like this. So hence, if okay. So I think I shouldn't write like this. So let me see how I rewrite my thing. Okay. Then sum of two square is either 0, 1, 2, mod 4. Hence, if n is a sum of two square, then n cannot be 3 mod 4. Okay, so there's no way for you to add up to 3 mod 4. Okay, is it okay? Okay, realize that now we are asking about sum of square, but the language we use is like congruence. Okay, so the congruence becomes some language already. Okay, yeah. But then we are trying to deduce different result than congruence, other than congruence. Right. Maybe let's go a bit further before we take a break. So next theorem is if you know that m and n are both sum of two square, then mn is also a sum of two square. Okay, so this is a very combinatorics proof here. So let's say we have a square plus b square and a c square plus d square. Okay, maybe you can try and expand this guy here and see what do you get. Yeah, maybe you can try and expand this guy. And can you figure out it is some square plus some square or not? Can you try? Yeah, try expand this guy up. Anyone expanded this term here? Finish expanding. What do you get? A square C square plus A square D square plus B square C square plus B square D square. Is it possible to write as a sum of two squares? Sorry? So what do you put here? AC, BD, AD plus BC. Does this work? Let's try. So A square C square, right? And then minus 2ACBD plus B square D square. And then A square D square plus 2ACB. Okay, anyway, plus B square C square. What? Yeah, yeah, good. Okay, or another, I think you can put sign in different places. You can do AD minus BC square plus AC plus BD square. Okay. Okay. So this theorem will be useful. I mean, this theorem will be useful in the sense that this proof here is we will use this calculation later. Okay, we're gonna use this calculation. So please be sure that you remember which one to pair up. So this saying that actually you just need to make sure one of them is minus. Yeah. So you can memorize this using some matrix form, right? If you know matrix. So this AD minus BC is like a determinant of this matrix here. A, B, C, D. How about this? Maybe you could turn your matrix around. So you swap it like this. A, C. But then you need a minus sign, right? You can put a minus sign anywhere on the diagonal. AC minus BD. Okay. Okay. Good. Okay. So maybe before we take a break, can I show you the Greek fountain? Can I show you Greek fountain? Maybe I show you what he does first, what people explain about him. And then maybe you can feel a bit related to what you have learned. So this is like 4 days ago. Yeah, 4 days ago. So you are learning something very trendy. Sound up. And
Subtract double with
I think this is the loudest 有的按哦，是这个。
equations have more than one unknown variable represented by a, b, x, y,
Like contain question.
and solution. Pythagoras theorem is a Diophantine equation. A squared equals b squared plus c squared. The whole number solutions for a, b, and c are called the Pythagorean triples, and there are infinitely many of them, starting with 3, 4, and 5. If we square them, we can see that 3 squared plus 4 squared equals 5 squared. But what if instead of squaring a, b, and c, you cube them? Not so easy to solve. In fact, the Laplace theorem says that there are no Diophantine solutions for a to the n plus b to the n equals c to the n if n is greater than 2. And sure enough, for hundreds of years, nobody was able to find any whole number solutions if n is 3 or more, if the equation has degree 3 or higher. But it took from 1637 until 1995 for Arvid Fowden and Andrew Wild to prove that there cannot be any such solutions for any n greater than 2. One way for mathematicians to understand the deeper patterns of numbers is to represent them as geometric shapes. This is the field of arithmetic geometry. Equations can be expressed as sets of points by turning the equation into a function and plotting the solutions as coordinates. So the equation x squared plus y squared minus 1 equals 0 can be expressed as fxy equals x squared plus y squared minus 1. And then we study where this function equals 0. If we plot this on a flat sheet of paper, it gives us a circle, passing through the points where x equals 1 or minus 1 and y equals 0, and the points where x equals 0 and y equals 1 or minus 1. Any point on that circle gives us values for x and y, which solve the equation. But those 4 integer solutions, which are obvious or trivial, as mathematicians would say, they are the only whole number solutions. But we can find infinitely many rational numbers that satisfy this equation. For example, x equals 3/5 and y equals 4/5 is a solution. So if you're prepared to make the numerator and the denominator large enough, there are an infinite number of rational points on the curve. They're called rational numbers, not because they behave in a sensible way, but because they can be expressed as a ratio between 2 whole numbers, also known as fractions. But far more of the points on this circle are irrational numbers, so-called because they cannot be expressed as a ratio between 2 whole numbers, though they may be approximated by fractions if you make the denominator big enough. That sounds bizarre. Think of the irrational number pi. Its true value cannot be expressed as a fraction, but for practical purposes, we can approximate it as 22/7, or 3.142, which is 3,142/1000. The closer we want to get to its true value, the greater the numerator and denominator need to become. This is Diophantine approximation. So that equation, x squared plus y squared minus 1 equals 0, has integer solutions, rational solutions, and irrational solutions. But if we change the power to 3, x cubed plus y cubed minus 1 equals 0, there are no positive rational solutions. Difficult equations involving both multiplication and addition can be expressed as curves in number fields. A field is a set of numbers with some rules for how the numbers behave when we add or multiply them or try to put them in some kind of order. The number field Q, for example, includes all the rational numbers, that's Q for quotient. Complex numbers, which include I, square root of minus 1, form the number field C. A polynomial equation includes different powers of the same variable, like x cubed plus 3x squared minus x plus 1 equals 0. And the higher the powers, the greater the degree of the equation. And from the degree, we could determine the genus, which tells us how many holes there will be in the curve. Elliptic curves are given by cubic equations, such as y squared equals x cubed plus ax plus b. So they have degree 3. That means they belong to genus 1. And the curve, defined by f x y z equals 0, has one hole, like a ring donut. Andrew Wiles used elliptic curves when he proved Fermat's last theorem. In 1922, Louis J. Mordell proved that the rational points on an elliptic curve are generated by a finite group of points that behave in predictable ways, an abelian group. But what about curves of genus 2 or more, described by equations with higher powers? Unfortunately, they don't follow such straightforward rules. Mordell conjectured that curves only have a finite number of rational points, but he was unable to prove it. In 1983, Gerd Faltings proved Mordell's conjecture, which is now known as Faltings' theorem. It was a major achievement, especially for one so young, and the beginning of many important results in number theory.
Yeah. So there's an idea of holes mentioned here. So you could learn it in algebraic geometry or algebraic topology. Yeah. Okay, let's take a break till 4:30.哎，谁？人漏看了，有看这里啊？
不是，我是在
OK，
我在这里写的，然后这里就这个 five 写了一个流程，
可以
证明自己的对。
那我漏了。OK，哎，你发给我，我帮你加。
是 five 键
啊，发听写。
哎，我的后面，哎，等一下，
全部 MP，
这个可以写掉，这可以写，这个可以写掉。我们没有写，我们没有写，
这个 A
啊，对，
我这里有写了，因为我是分成两个来认的。
啊，你的 A 是23。
为什么没推？
不是，这只是个例子。
对，我们需要一个例子。
对，这是个例子。
对，需要这个例子。
然后我最后有写 A。
对，我要的是这个例子。对，我要的。
那我看答案也是有写
对，
A。
因为如果你要证明它是 maximum 的 possible， 你先证明它可能会到这里，然后你再证明它有一些 A 它会得 order， 对，所以我需要这个。
我跟你讲，
给我 check 一下，你这个 A 对吗？
还做什么23？
我觉得我是3。
然后我是分成两个来证的，是一个。
什么意思？
就是我看一下，我是分2的5次方跟3的3次方，就分成这两个来证。
对，
就这样子。
对，这个我明白。这个我明白。只是说我需要那个例子，其实
是要全部的 A。
不需要全部啊，就是只要有一个就可以了，因为你要 possible 嘛。
我都写。
对，I mean like 我重点是因为它是 maximum possible 嘛，所以要证明 possible 的话，
就是
需要有一个例子啊。对，好像没有检查过，检查一下。
跟强的哈，挺麻烦的。这是可以的，因为它有理论。
我几还是864呢？我查一下。好像不太对耶，23会提早去1，它36就1了。看看你怎么算。
我是算的。
对，看看你有没有算错。
看看，这是2的5。
3的3呢？
3在这里。
它18罢了。 你怎么去到72呢？
你看等一下，
呀，
这个是8，你得
现在有啊，就是还有说他违约还这一次也是一次过发。
对，
嗯
就
还是跨两边呢。
就是2的5，它肯定是8出现了，
对，
对
那
吧？然后
另外一个呢？
这18出现了，
对，会不会有算错？
是前面吗？
对，因为他36，哎，他这边写36吧，所以是除一半哦，一半就可以解决掉了。所以会不会这里9就应该其实就那个，我看一下，OK，我们分开检查。What's the order of 23 mod 3+3 maybe？我们检查这个。
哎，你的钱很大个，可以装人气。
18，这样这个是对了。OK，另外一个，
有人没事，
对啊，干嘛？
没事，
你也玩吗？
我也玩，
哦，你也玩，你什么东西？
70多个星，
我操，你很强诶，太强了你！
是的，是的，
我是谁？啊，sorry，
32，
5啊，
嗯，
哎，32，sorry，
就是2的5次方，
打错了，哎，23还是32？哦，没有，25哦，你是说2的50方是32？OK，
嗯，
啊，这个一次就解决了，其实这个算错了，这个算错了，你试试看看
行，
，9981，你试看，但是如果你有试的话，我可以给你 maybe 多1分啊，呀，因为至少你有 try，没算错吧？OK 了，其实你算对一半了，其实。
你就这个例子记错了，
所以这边错了，可以给你2分吧？
对，
你 screenshot 一下，你发给我。
有 Teams，
OK，
好，谢谢老师。
太神仙准确，这个有看出来。是不是？会确定有人说对呀，一样都一样。我跑去浪费那时间跑去打街，打街不是3天4天，至少5天都错了20，然后跟摸着了。我觉得还好，我没有读啊，浪费时间。等会怎样做好的？然后我是要看什么才会去老师，练一下自己的能力。也是跟我在一起看个片，那个时候我就送个大盘咸鱼，我是吧？然后我想对吧？
这个为什么克隆？
为什么克隆
这没有说一定要找 A 啊。
possible 的意思就是说一定要找 A，因为 possible 的话，你要证明它是有可能的。
什么意思？就是我把这个求出来还不行，还要把对应的 A 给求出来。
对，因为对，
好吧，
因为 possible 的意思是
可能
可能，就说你要证明它可能，因为如果你找不出，它就不可能。existence 的 statement 你都是要找出来，或者你说找不到的话，就有 contradiction。
如果你老师看老师，对，不要给老师压力，别给老师，你不要让老师给老师压力就好了，不用压力。这个都是个好像我们谢。是因为我太早去了，可以。手拿一下，我这边拿过去。 我看我就不需要。
哎，哦，对你没有写出来的话就，你没有叫你把那个 A 和 K 写成那个，
表格。
对，
可是
有写吗？
这是表格不是这个吗？但是这是这题啊。
啊
为什么？
？What？怎么跑到上面去？怎么？喂？什么？诶，什么情况？
就是有 A 呀、
喂，哦，这是谢，OK，我以为是这一题来的，OK，好，你截个图，你发给我，你截个图，你发给我，
这个呢？
这一个你需要去找一个 A 来证明说这个 maximum possible order 是72呀，
就是
就是你要找
例子
对，要举个例子，等一下我们会讨论。OK， I'll take the attendance. What day is yesterday? Yesterday is 24, huh? Today is 25. 苏月，欧苏月，苏月 here 呢？杰森是杰森，方家豪，陈炫，洪婷，蒋泽，OK，任波，OK，易航，思颖，思，OK，曾贤，邓俊，OK，叶伟通，OK，陈子涵，王金珍，洪一佳，陈子，崇瑞，思曼，陈思曼，OK，嘉诚，丁真，浩宇，浩然，心仪，温琪，小柔，泽瑞，海莹，Tiffany，OK，Jakib，Yasin，OK，they all here. Judging, OK，嘉悦，德兴，明涛，旭晨，亦飞，曾亦菲，玉清，李林义，华园，曹化园，王雅，OK，有点上面有声，交了，其实交了，好，等一下看一下。
像我们那个这个竞争，我都会整个速度都有方法的，我一块
怎么了？
呀，查一下，早上我查的时候还没有哎。
啊？
这个上去凌晨，去做
New Summit，
做每天也是电脑的，先不首先这个。
哎
是没？
哎
是没？我早上开的时候没有。哎，没有。
啊！
我
我记得我哎，但是
我不是有发提醒你。
我记得当时就已交了，
哦
当时回完之后就交了。
OK，
那
没有。
那我现在发给你，再发一
你
个。
再发给我。好，你发进来之后，
这上面你写完，那你要看时间吗？
不用紧，我看你答案我就知道是什么时候写。
OK，
你现在发给我，你现在发给我。浩聪，李浩聪，刘艺书，子良，OK，甘金浩，郭明忠 Wihan, okay. Ayub, Joy Lee. Okay. So you guys good friends? Don't know each other? Don't know each other? Seriously? You guys sit together always? Huh? Her Ming Hao. 黄子琪，黄妻子啊，sorry. Why you raise up your hand? Sorry. 秦子祥，OK. 熊培成，新宇，OK. 瑞敏，赖文义，陈志，陈子睿，李小华，曾天健，Aaron Fabian，瑞全，OK. Isaac 宾科，高硕，OK. 诗涵，诗怡，明显呢？明显啊，明显没有？不是吗？OK. 你们是不是其他课又有 presentation 啊？有啊，
还有他黄色的话，只会来一堂啊。
双分心灵，嘉凯，卓娜，家福，冲扑，武艺，崔文谦，汉旭，郎坤，小嘉怡，赵泽宇，周希，陈少涵，陈卓，李乐山，彭奕晨，赵星辰 ，No, I think I saw No 为什么 ？OK， 玉涵，玉兴，沙丁。什么？
老师翻到完。对，我们讲完了，不可以一直赶一下啊。
对，好，非常好，努力一点。
老师可以约老师。
我努力过头啊。努力过头啊。OK。喂 ，my phone。
可以退反。
Okay, right. So this one. Can you solve this? With what we have now. Okay, we know that two things is a sum of 2 square, then the product of it have to be a sum of 2 square. So this number is so big. Is it possible to like just randomly guess which sum of 2 square? Can you use the previous theorem to find it? Huh? 13. Oh, what how? Very good. So one way you say is 13 and 1. Like this. Okay, maybe this is lucky. You can quickly find it.
注意到。
But then can you use the previous theorem to help you to break down this problem? You think, can you think of a way to break down this problem? Huh? So So how to use previous idea to solve this? So let's say if you can write these two as a sum of two square, then the product is also a sum of two square. Yeah, sure. Okay. So if you can break down like this, then the smaller number is easier to find the sum of two square, right? Because less choices to make. Okay, for example, 我忘记你的名诶，已经最后一周了，我还记不起你的名。你的名叫什么啊？你是红婷嘛？对不对？刚才谁说10是1+9啊？他是谁？啊，香泽，朱香泽。对，朱香泽。Okay, so 香泽 says 10 can be written as 1 plus 3 square, right? Okay, but 17? How about 17? Huh? 1 square plus 4 square. Okay. So you can compare, right? Is it easier to find sum of two square for a small number or a bigger number? So if I know that these two, okay, so these two are the sum of two square, the product is also sum of two square. So we're going to use the formula just now. Okay, the formula you told me, what AD minus BC, and then the other one is AD plus BC. Okay, so make sure you swap all the possibilities. Okay, so we will use formula, this formula. Okay, I'm going to use this. You can try this. I think it's the same thing. So AD minus BC, you will get A dot 4 minus BC 3.1, right? Square plus AC 1.1 plus 3.4, right? Square. So what do you get? So 1 square plus 13 square is the same. Okay. Yeah. So instead of guessing or try and error, you can use the theorem that we proved just. What do you mean? So 不同的上不 square 上不难。我们加上了有很多的数，然后这样才可以把每一组都算出来。你说 different sum of two square，对。Don't think so 了，不行。好的吧？我不确定，不确定。我觉得。I mean, for this case, maybe just for this case. Okay, is it okay? Get the idea? Okay, so the previous theorem can help you to split up. You split your numbers maybe into primes or other factorization. Then you see that whether those can be written as sum of two square or not. If can, then the product will also can be written as a sum of two square. Okay. Next, how about this? Wanna try this? I don't even try this yet. So shall we try this together? Huh? Got idea? Oh, I got idea, huh? Wait, Okay. And what do you get? 29, 23. How do you get us? How do you get 29 squared? 22. What do you use? 13 times. 13. Oh, okay. Sorry. So how do you get this? Oh, so you use your AD minus BC, is it? So it's okay. So you get this one plus this, and then this one minus this. Okay. How about the rest? You get different solution. You get different solution. Any other solution you get? No. Okay, so after you calculate, right, you could do some sanity check here, right? You could explain it and then check whether you get the right sum or not. Right? Okay, calculate. Like 131 squared, and then add up with 7 squared, and this one should be 1012. Yeah, so you could do some sanity check. It's very good that I saw some of you in your assignment. You really do checking for your answer. Yeah. So yeah, not just now, Sam ask whether these are only or maybe depend on how you split up 10 and on split up this 10, 10,000, 1,010. Is there other way to do it? Anyone try like 5 times 200 and maybe like this also can, right? Correct, because this can be written as 2 square plus 1 square times 1 square plus 1 square, right? And then you can put this. Okay. Yeah, you want to try this? You want to try this? See whether can get different. Hey, why my screen lag? Yeah. Maybe you can try this. See, you get the same sum of square, or you get different one from that one.
Oh,
Okay. You could try. Yeah. 是的，算完了。12、20、2呀。11的平方回来。So you mean you combine the last two become what? 11 square? 9 square, okay. And then did you get different sum of squares? 13、29 ，OK。
那应该就是所有的解了吧？有没有可能是
I don't know. I haven't proved it before.
I don't know. So they are suggesting that these are the only two you will get. But I don't believe. But I don't believe.
I haven't proved it before. Okay, maybe I can try to think about it.
If you are so interested. Okay. How about you combine the first two? Okay. I think you combine the first two also what we had, right? If you combine the first two first. 101 is a prime, right? Is it a prime? It's a prime, okay. Could you split this prime in a different sum of square? Different sum of square? Yeah. Is it possible? Is it possible? In that case, you need to try like all the prime, unlock all the perfect square that's less than 101. So that's why I'm listing this guy down. You need to get one. This one is kind of tricky, right? So maybe you get from 81, but if you get from 81, you need a 20. 20 is not a perfect square, so it's not good. 没有 huh? Yeah, I don't think so also. Because if you get one here, this is not enough. Never mind. Okay, so far okay or not? Sum of two square. Okay, yeah. So you can split into factors and then try to figure out the factors have sum of two square or not, and then you combine them together. Okay. Next, why are we talking about this lemma? Let me see. Okay, so this lemma will be used to prove the theorem later. But let's see what's the lemma, what's the content of this lemma. If P is a prime such that P is congruent to 1 mod 4, then there exists an integer K that squeezes between 0 and P such that K times P equals to x squared plus y squared. Okay, so this theorem, this lemma is very special. What this lemma is trying to do is, if you are prime, okay, so if you are prime, what's the possibility mod 4? Either 1 or either 3. Okay, but 3, we say that you cannot, okay, if it's not, okay, if you are 3 mod 4, then you cannot write as a sum of square, right? So we don't really care about 3 mod 4 already. Okay, so if it's 1 mod 4, then it didn't say that P can be written as a sum of square. It just says that a multiple of P written as a sum of square. Does that make sense? Multiple of P. Okay. And then this multiple is in between 0 and P. Some multiple of P can be written as a sum of squares. Right. Now we prove this. You see. Okay, so maybe we can prove this to show you that what we have learned before is really useful. Okay, this process is very easy. So first, we learned that. Do you still remember the special things about 1 mod P and 1 mod 4? You do last assignment, right? 1 mod 4, what do you get? If your P is 1 mod 4, is a prime. -1 is a quadratic residue of P. Okay, let's gonna show you how this gonna be used here. So what does it mean by quadratic residue again? Meaning you has a solution. Okay, solution to what? Solution to this following congruence here. Okay, so there's one integer less than P such that a squared to congruence to -1 mod P. Quadratic, right? You take quadratic and then left over is -1. But then what is mod P? Combined with your chapter 2 or 1 about congruence. It follows that a square plus 1 equals to kp for some multiple. Okay, so what this says here? So hence, we found x and y such that sum of their square is kp. So what is x and y here? So we just pick our x to be a and pick our y to be 1. Okay, but then we haven't shown that k have to be less than p, huh? So the last thing we're going to show is why this k is less than p. So so we will see from this following inequality here. Well, so we know that kp is equal to x squared plus y squared. But then at the same time, we know that x, so this a here, okay, we know this condition here. So we're going to apply this condition. So this condition says what? This a here should be less than or equals to p minus 1 square. Okay, but y, we already know what is it, right? Y is 1. So 1 square is just 1. Okay, so this guy is 1. Okay, so if you expand this thing out, expand this thing, p square minus 2p plus 1 minus 1. Okay, so you get like, well, this term is like p square minus 2p. Okay, but what is p square minus 2p here? Okay, I don't really care, but what I care is this thing is less than p squared. Okay, so you get kp less than p squared. So you cancel p on both sides, k is less than. Okay, so we see that kp less than p squared implies k less than p. Does it make sense? Okay. Yeah. Okay. Because x here is a, right? A is less than p, so less than or equal to p minus 1. Less than 5, so less than or equals to 4, for example. Any question on this? Okay, so the special part of this proof is we can even control this multiple, and just by looking at this possible solution. Actually controlled by the possible solution. It turns out that the x and y that appears is very simple, okay, from this correlate residual point view or point. Obviously, if we written like as such, there could be other ways to obtain x and y here. Okay, this is just one of the ways to obtain it. Because this proof is about existence. Okay, I just need to find one for you. It's enough. Okay, existence. Okay, so from here, we could prove that if P is a prime such that P congruent to 1 mod 4, then P can be written as a sum of 2 square. Yeah. But then this theorem is not gonna prove for you. Okay, I just include as a inside the note. Should we prove to you? Yeah, maybe not. Okay. So this gives a very good necessary condition that when you can write a prime number as a sum of 2 square. Just now we look at 101, right? Okay, 101 is a prime. It's also 1 mod 4. So we have managed to write it as a sum of 2 square. So corollary is if P is a prime, then P is not 3 mod 4, then P can be written as a sum of 2 square. So I mean, this is a restatement of that theorem because if you are prime, there's only 2 possibilities. You are either 1 mod 4 or 3 mod 4. So these 2 lines is the same thing actually. But then what's the significant thing about this is, remember that just now we have a condition that a necessary condition that if n can be written as a sum of 2 squared, then n cannot be 3 mod 4. Okay, so let me write down here. So previously we have n positive cannot be can be written as sum 2 square implies that n cannot be 3 mod 4. But then this statement says that if n prime and n not 3 mod 4, then so arrow like this, then p can be written as a sum of 2 square. So can you see the arrow direction here? Okay, so this part is the sufficient condition. Okay, sufficient condition for p to be written as sum of 2 square. But then this part is the necessary condition. So necessary condition meaning if you can write as a sum of 2 square, then it is necessarily that n cannot be 3, 4. So meaning what here? How can you go backward? How do you go backward here? So if you're gonna go backward, you need to add a prime condition here. Okay, so for prime, then this statement is if you want to go backward, you need to add a prime. Make sense? So if it is a prime, then 3 mod 4, that it cannot be, it can be written as a sum of square. Okay, good. All right. Shall we try some examples here? Okay. This number is kind of bigger. First, can you identify this as a prime or not? Is it? How do you test it? Sorry? Square root of what? Or you try square root 1153 and then you try all the possible divisor. Okay, okay, good. Okay, good. What's the nearest perfect square? What's the nearest perfect square? Yeah, I think you also can figure out from your square root 1000. Huh? What? 8. So 1018. 1018. This is a perfect square. What's the nearest perfect square to 1153? 1156? 1156? Is it 1156? Okay, yeah, okay. So square root of this guy is what? 34. Okay, so you need to like test about 34 of them. Okay, so then you figure out that this is a prime. That 1153 is a prime. And then it is also 1 mod 4, right? How is it 1 mod 4? Because it is 288 times 4 plus 1. Okay, so it's 1 mod 4. Okay, so by previous theorem, you can write as a sum of square. Sum of 2 square. So how do you write it as a sum of 2 square? So it's a prime, or you cannot split it, huh? You cannot use the method we do just now, right? Because how you split prime is just the prime itself. 1. So you're gonna do try and error. But how many try and error you're gonna do? Well, you can use the method that we prove for how you prove that something is a prime. If you still remember how we reduce it to square root n, square root nearest perfect square. You still remember how we consider that? So in this case here, suppose without loss of generality, x less than y. Do you guys know what is this? Without loss of generality. Okay, so why do we say that? Because I assume that I assume that x is less than or equals to y squared, because in reality, maybe y could be less than or equals to x. So, but then doesn't matter because you can rename them. Okay, so that's why that's why we say without loss of generality. So in reality, it could be that y less than equals to x, but we could just rename them. We could just rename them. Rename. Okay, so from here, if we assume that x is greater or equal to y, what does this mean? This means that x squared plus y squared should be greater or equals to x squared plus x squared. But then this is just 2x squared. Then what does this mean here? So this gives a restriction on x already. Okay, so can you see that our x get restricted to something less than or equals to 24? Or should we do step by step? Yeah, let's do step by step. So 1153 greater or equals to 2x squared, and then x squared is less than or equals to 1153 over 2. Okay, and then x is less than 115 square root of 1153 over 2. But then you give me a nearest of x squared, right? Okay, so maybe we take 1156 over 2. Is it good? But then I only can take square root of 1156, right? But I cannot take square root of 2. Is this better? Should you calculate using calculator, or can I work out a clever thing? So if I do this right, it's 34 over square root of 2. Is this any better? Or maybe, let me think. Or is this better? Square root 5. Oh, doesn't matter. It doesn't matter. Okay, so can you figure out this? This square root 1. 24. Huh? 24.01. Okay. So maybe we could say that because this x should be integer, right? It should be less than or equals to 24. Okay. So you could try 24 square can pair up with any square would get this. And then I think there are 24 to try. Okay, so this reduced significantly. Right. Okay, so sorry, yeah. So by try and error, luckily if you try from 1, maybe it's not too hard. It's x squared plus 33 squared. Yeah. 至少你不要吃到太大的号。万一要吃到太大的怎么办？不会啊，因为最大的23。对，那不还是要24个样子？那如果没有24的话，你从哪里会吃？33我差吃了。Why？ 因为这是它的平方，33的平方，那这两个再想想。What do you mean? 30? You mean found the maximum of x squared? Yeah. 33 is the maximum, right? You mean 34 already greater than? Maybe in this case you are lucky. Maybe in this case you are lucky. Since this one is maximum, then you manage to find it. But in other cases, I don't know. But then this works for any case, right? This should work for any case. Okay. So this method, did you notice that this is how we figure out? We just need to check for square root and check something. So yes.
它这个满足所有情况。是的，我的没有。就是用哦，错了，
对，OK，so far，OK，OK，shall we try next one? Yeah, how about this one? Oh, this one. What do you think? Maybe you can tell me what you should do. I mean, what will you do? Yeah. You cannot just multiply anything into the sum of square, right? Because turns out that this 9 is a perfect square. Correct or not? Okay. So let me show you. Okay. So okay, so what Xianze say was because we know that we just split 115 into sum of two square, right? So this is just x squared plus 33 squared, okay, times 9. But then turns out that this 9 is a perfect square. Okay, so we could like multiply 3 squared to x squared, multiply 3 squared to 33 squared. Then we can just combine the base number, right? Because their power, their index or their power is the same. Okay, so this becomes 24 squared plus 95 squared. Okay. But in general, you can't do this, right? Because if it is 8, then how do you split your 8 into square? Then maybe you need to try the method that we had just now, right? Try to break your 8 or other number into sum of two square first, and then you take the product of sum of two square. Okay? Does it make sense? Yeah. Okay. Or if you want to make my method general, actually, you should think of this as x squared plus 33 squared times 3 squared plus 0 squared. Okay, then you can make my method general. Or this will include what Sandra said. So sorry, the screen a bit lag. Yeah. Okay. Or you can realize 9 squared as a 3 squared plus 0 squared. Then you use your product of sum of two squared, then you will get this thing. Okay. Because one of the terms you multiply with 0, right? So that's why you only get one term from each. Okay. Okay, so far so good. Good. Okay. Very good. Okay, good. Jia said very good. Okay, next one. So the positive integer n is the sum of two square if and only if each prime factor n of the form of 4k plus 3 occurs to an even power in the prime factorization. Okay, so this gives another actually necessary and sufficient condition if and only if. Okay, so it's equivalent in this case. So if you want to write as a sum of two square, because just now we cannot give the backward error, right? If I give a backward error, I need it to be prime. But now we give you a backward error. Okay, I mean front and forward equivalent condition. That is, each prime factor n in the form of 4k plus 3 have to have even power there. Do you still remember about this 4k plus 3? 3 more 4, right? Okay, just now we say we ban 3 more 4, right? Okay, but then if you have a prime factor of 3 mod 4 to an even power, then you can always write it as a sum of two squares. We're not going to show you the proof, but you're going to see it as an example. Okay, how about we do this after the break? Okay, I can let you think a bit. Let's do it after the break. Okay, let's break until 5:06.
不要生病，一生病的话，我是没
上一个这个就是这个 if 对对，就是我看那个课堂笔记，就是这边就是这么来的，那我要学，因为我还没看到有例题。
没有没有，不用不用，他只是告诉你这个 conversion 的怎么说，它的重要性。
就是因为没有例题，所以就是那个做题是用不上的。
啊，是对对，还没我们没有关于那种题目的关于那种东西。
就是包括这个也是，
对，没错。
看起来就很复杂。
它是看起来复杂，它的意思其实就是说，它的意思就是有无限个有理数，会 e over q square 的接近 alpha，就这样。
但它这个 Q 不是是随便取的吗？
随便取，
他说是因为是那个无限多的，
不是随便取，不是随便取
就是我的意思是这个 Q 是无限多个
啊，这 q 啊，对，没有错，这个 q 是无限多个。
那它这个小于一个 Q 分之一。
怎么说？怎么说？
哦，也没问题，没问题。
其实这些都是从这里来的，就是这个 k conversion 来的。其实，因为 k conversion 是无限个嘛，你会1、2、3到无限个，你就一直加你的 a n，就这5000多个。
然后就是那个昨天上课的课件还没有传到的
啊，对，我还没有更新结束，要完了，我今天要上传。
今天，那我就今天晚上复习。
可以，
然后这一口是一直在跟着，然后现在还比较好接受这样子。
没问题，很好。
谢谢。
睡不着。但成日乜唔亏錢啊？即係我是打機。是零食才看起来的这个。为什么这样？应该没事。然后我到底是还没有。都遇到这种主动选择题啊，也想哪个你会比较开心，哪个你太开心了，选择这个大题。我早为什么家里会去那样？我们朋友。好，那个体制的看到我为什么吃了就是在很多人看到发现吃点大碗，然后我去用。你还真不去看，对吧？因为你的帮我去做。还我不是。还是城隍里面。对呀，城隍行城隍行。我们的是我们的那边，我们的那边。我们讲。我不好说，应该他们考虑到。我来想说。下去，不是这样子的，那么就保持下去，不要少，不少，也是环境。你可能需要一个是一部分，要么你看这个吧。我会继续这样，好点跑还是这样。还是亚这类的，就于虽然不是啊，我吃了一个200岁。 就是好说，生怎么看到呢？哦，OK OK。没醒来了，你这里忘记了啊？没东西。如果是搞两个老师的靠着体育孔融啊，说服上去就不讲。没有不一样，对吧？要玩的是水啊，可以的。一般自动sen色，全部人是的是这样，都没打点开点，不能点全部散。如果还有这样子你怎么可能把3个是啊？我觉得累，你是8个眼睛摆一个。是他这个是感觉有吧？我才2分钟，看到我也是有一点点。但是有可能是真的不要特别做一个网站可能也行，这个开早上开早上调开门。每次早上起来要醒到去冲我在冲一起其实我是7班只要是给他去穿一种法文科200块钱考文科已经200一个阶段性，以前就很早就起来，然后之后也是很起来，现在那种就他们解释，在之前看那种真的是整个看起来更这个习惯我跑到一圈就开始，然后到后来就不要看了，我们要谁睡了？那水面非常清楚，没有我还没到。没有啊，加油！我声音很大，期待到特地开大声了。你看他的哇，他开大声，然后他玩了，我就大家也打开心啊，就这样开。真是终于有坑到了。
Okay. So let's come back here. So just now, remember we say that if n is positive,
it can be written as sum of 2 squared, then n cannot be 3 mod 4. Contrapositive means if n is 3 mod 4, then it cannot be written as sum of 2 squared.
so n equals to 3 mod 4 is a problematic state. But then if it appears 2 times or even times, it is okay. Become 1? What do you mean? Oh, you mean 3 times 3 becomes 1. Makes sense. Yeah. Okay. You think of that. Yeah, I think like that makes sense. But then I can show you directly how the computation becomes. Okay. Yeah, I think you think of that is making sense. Okay, so let's use examples to tell you how to do that.
So if you realize in this prime factorization, right, you realize that what do you realize? 11 is 3 mod 4.
And then 19 is 3 mod 4, right? But if you go back to the example we started this subsection here, where is it? I think too far away. You see, 11 and 19 is not sum of two square. Okay. Okay. So 11 and 19 itself you cannot write as sum of two square. But then square turns out it's okay. Okay, so how is it true? Okay, how is it true? So let's see. In this example, I'm going to tell you why it works. So, so if you look at these examples here, okay, for those that I cannot split out, right, I throw it to the end first. And like this. Okay, can we write 13 as a sum of two square? I think we did it before. And then 17, we also did it before. We did it until 20, right? Okay, like this. And then we can combine the product of sum of two square, right? Okay, we can combine it. Okay, 3 times 4 plus 2 times 1. For example, and 3 times 1 minus 2 times 4 square. Then this will become 14 square plus 5 square. But then what do you left with? Okay, so this is sum of two square multiply a square. I think we met this just now, right? So what we're gonna do is just push the 11 times 19 into each terms here inside the sum, like this. Does it make sense? Does it make sense? Okay. So this trick actually you see it before already. So this trick you see it before. Yeah. So if you can imagine this different even power, right? That means you can push it in a different way. And yeah, you push it in a different way. Does it make sense? Okay. Yeah. Okay, so far so good. Before we leave sum of two square. Yeah. So the next thing we're gonna do is sum of 3 square. No, not sum of 3 square, sum of 4 square. Because sum of 3 square is not nice. Okay, let me show you first why sum of 3 square not nice. Okay, let's do some motivation. So maybe a natural question to ask is, can we do sum of 3 square? Okay, is it possible? Yes, into sum of 3 square. Okay. I mean, you could, but then it is quite restrictive. For example, 7 square. Okay. Is this what I wanted to say? Let me see. No, not 7. So I should say 7. Okay. So let's say I want to write 7 as a sum of 3 square. Is it possible? Huh? Is it possible? No. Okay. So I think a few possibility you could try is sum of 1 square, sum of 1 square and 2 square. Maybe there's the few you could try. Okay. Yeah, these are the few you could try. And then more than that, you'll be getting something greater than 7 already. Yeah, so it's kind of hard. Okay. But then we will prove some stronger thing is we could write. Let me see. Hopefully I don't say anything wrong here. Let me check first. So what's the stronger thing we could do is every positive integer can be written as a sum of square of 4 integers. Okay, if we increase one more choices, give you 4 choices, then this can hold for all integers. Very strong. Every integer can be written as a sum of 4 square. Hey, do you guys want to continue this section or you guys want to discuss assignment? I forgot the assignment already. You want to discuss assignment or you want to continue this? Continue this? Okay. Then maybe we can discuss assignment on tomorrow. Tomorrow. Okay. We'll do it on. Okay. So let's continue on this. All right. So this subsection we will try to prove that instead every positive integer can be written as a sum of 4 square. So just now we see that 2 square integer doesn't work, 3 square integer doesn't work, but if you increase up to 4, then everyone can be written as the sum of 4 square. So we include the choice of 0 here. 0 square also included. Okay, so let's try. See how we build to this examples here. I mean, this strong statement here. Okay, so first theorem is very similar to the sum of 2 square. But if m and n are positive integers that are each of sum of 4 square, then m and n are also. So can you imagine what you need to do here? You imagine first. Can you imagine? Can you imagine? Try and write down what this sentence trying to do. Can you imagine? So you have a square, b square plus c square plus d square, right? And then e square plus f square plus g square plus h square, right? Okay. Then what is mn? What's mn? Sorry, a bit lag. What is it then? Okay, so there's a big chunk of products here. Okay, there's a big chunk of products here. Okay, I won't torture you to find the formula. I just give you the formula. AE plus BF plus CG plus DH square. But it's almost the similar idea here. It's a similar idea here. Almost. I'll say almost. So if I give you this formula, what can you like relate? What can you relate back to the previous formula? It is kind of like taking all sort of all possible products between terms. Is it okay? Wait for the last one. So you see AE, AF, AG, and AH appears. And then B will also combine with all the EFGH again. Similarly for C and D. And then there's a alternating sign happening here. Okay, it seems that there's a rule that governing this sign. Okay, there's a rule governing this sign here. So let's us go back a little bit to this case here. To the previous case. Maybe that case is smaller. I told you that you can think of determinant, right? So there's another way to think about it, which is using complex number. Okay, you can actually think of this product here as a coming from some complex number. So meaning, if you make it into some complex number, right, it will tell you how this minus sign comes. Yeah. Okay. So what is a square plus b square here? In mathematics, right, we would think of this as a length of something. Like I told you, right, Pythagoras theorem. C square equals to a square plus b square. So this is the length of that c. Okay. So this is the length of something. You can think of this as a length of the complex number. You guys learn complex number before you come to university. Did you guys learn? Yeah, okay, good. So you can think of this m as a product. Similarly for n. Okay. Then
if you multiply these together, then this is exactly why you get the and then the I will disappear. Okay, the I will disappear.
Okay, the item will disappear. Okay, if you follow this calculation. So should I compare to your calculation just now? Did we do calculation? Okay, maybe let's write down here, see if it is easy to get it or not. Okay, so if you try and multiply the items up,
They should cancel each other.
I do multiplication here. Mm, is it obvious that the I cancel? Let me see. What's the calculation they make? Okay, so what they did, what they do. So they combine like this. Is it easier to see? AC minus BD. Oh yeah, sure. Oh yeah, sure. Okay. So you see, so if they combine like in this way, so okay, so let me write now. So MN is A plus BI times A minus BI, right? And then times C plus DI times C minus DI. Okay, so what they do was they combine A plus BI and C plus DI first, and then they combine A minus BI times C minus DI. Okay, turns out that this one is easier to see
In the sense that the item that produced from both sides, right, they will cancel. Canceling out. Oh, no canceling out. But they produce a conjugate terms. Yeah. Okay. They produce a conjugate term.
So can you see this calculation here? So this term and this term. Okay, so they produce this conjugate term AC minus BD minus AD minus BCI. Is it? Let me check. Yeah. Not quite, huh? Not quite. Not quite actually. I don't know. Okay, never mind. I think they just expand now. Yeah. Yeah, sure. Yeah, sure.
两个 note 整起来可以把 note 给要写中间。意思
啊
就是两个和整起来就可以直接外面画一个大那个。assume that A 加 B I is W 然后 C 加 D I is Z 然后 M N 就是 norm of W。
Yeah, sure.
然后 this one is 就 norm of W to Z。
So okay. No, I was trying to say that I thought this is a conjugate for this, but it turns out it isn't. But then what is so nice about this relation? Yeah, so I was trying to think about why this calculation is good for seeing this. Anyone can see it. Why is it good? Initially, I thought that this multiply this will just get this, but
Let's just keep going on first. Okay, write down what he's saying. I was trying to see the logic this calculation trying to do. Okay, let's write it down first. Okay. So we got AD minus BC on this side, but then there's no AD minus BC on that side. But then you should see an AD minus BC. This one is an AC plus B. So this that term there. But that term is a negative. Let me tell you, supposingly, right? Supposingly, if it is nice, maybe it should look like this. AD minus BC squared and plus AC plus BDI. Then this will be easy to see why it is true. Correct or not? Okay, if I write it this way, then this is true, right? Because this is the like what I can say, it's a norm of this complex number here. But then this term is not that term. Then why do you complain like this? Let me see. Yeah. Oh, I see.
Just say把这个在那边。
See. But in this way,
这个的话是那个平时是吗？
yeah, that's what I say, right? So this one, if this form is easy to see, right? This form. But then in that form is still hard to see, unless you expand it. Yeah, that's what I meant. That's what I meant here. If in this form here, okay. So okay. So how do I realize this? So in complex number, right? In complex number, I'm not sure you remember or not. Maybe the norm of mn should be the norm of m times norm of n. Is this what you learn? And linear algebra learn complex number? No. No? Oh, this here no learn. You guys didn't learn. Okay, never mind. Let me see. Let me see. Length of complex number. Okay, so here. Okay. So if you learn about complex number, right? If you take a product of complex number, you compute the length. Actually, is the product of the length of two complex numbers. Okay. Yeah. Okay. So in this case here, this is a norm of this mn here. So this mn here actually is the norm of a plus bi times a c plus di. Okay, but then you can combine them together. Okay, and then this is the norm of AC minus BD plus AD plus BCI. Okay, yeah, then from here you can get this term here. Okay, yeah, so if you learn complex number before, then maybe you are okay. So how about sum of 4 square? Okay, so how about sum of 4 square? So there's also a number system that relate to 4 position. Can I say 4 position? Like 4 dimension. Because complex number is like 2 dimension, right? A plus bi. So There's also one number system that relate to 4 dimension, which we call the quaternion. Okay, so quaternion. Let me go down here. Okay, so this, this, where's this? Okay, maybe use this one because I got the notes here. So this is something that we relate to quaternion here. Okay, so there's not just I, there's a J and K here. And then I, J, K will satisfy this property here. So again, they will square to 1. Okay, it's like a complex number. So you can think of a complex number in 3 different directions, I, J, K. And then how they commute? They commute with sign. Okay, they don't just commute like IJ become negative. Then if you plug this into as their norm here, do the similar calculation. That's how the negative sign pops up. Yeah. Is everyone okay? I will use the word norm here, or the length of the vector. Yeah. So last time actually I briefly tell you, right? If you multiply with your conjugate, you get something as a real number, not real number, positive number, sorry, positive number. Yeah. Positive number. Okay, so it's a length. So if you multiply with a conjugate, you will get some length. Okay. If you don't get it, also doesn't matter, but then you can think of that. Why this minus sign occurs is because we related to some complex number or some different number system. Yeah. Okay, that's why there's some minus sign here popping up. Okay. Yeah. Okay, if that doesn't matter to you, also never mind, but you need to know this formula. Okay, you need to know this formula to help you do calculation. This formula I think is a bit hard to memorize. Yeah. Hopefully it's not in your final exam. If it is in, maybe I can convince them to give you this formula on the spot. Okay. Okay, can is this a deal? If this formula appear, I ask them to write on the board for you, okay? Hopefully no. Okay, you don't need to memorize this. If you cannot memorize, I will convince them to write this on the board for you. 我就说不用背。呀，如果真的考出来，我叫他们写在黑板上面。Okay. Okay. How about this? Oh, try this. Is it possible to do this? Yes, sir. How? You just guess. Huh? You just guess? No? Oh, 讲不了猜吧 Okay. Conjecture. Is it possible to guess or based on what we know previously, what can you do? You can split it into products first, right? I think it's not many products you can try, right? Maybe try 7 and 10. Okay, can you write 7 as a sum of 4 square? Also not many choice to do also. 2 square plus 1 square plus 1 square plus 1 square. Okay, how about 10? Is it possible? Also not many choice already. 2 square plus 2 square plus 1 square plus 1 square. Okay, then you can use the formula to combine now. Okay, so let's see who faster. Make sure you don't mix up with your sign. Mess up with your sign. Oh. 什么？我就是抄的，你还讲抄？你讲的。Okay, so we get that x square plus 2 square plus 1 square plus 1 square. Okay, so you can do sanity check here. Is it true? 64 plus 4 plus 1 plus 1. Good. Yeah. Okay. Yeah, so please make the sign right. Okay, so this is for this part here. Yes. 什么？零可以，可以。
那我如果直接就是写成10，然后
哦，你是说，比如说啦，你是 sum of two square，然后在那边加零加零就好了。OK，我要叫我的老师小心一点，可能要改一下题目。
non-zero。
呀呀，对，一定要嘛，对不对？
就搞两个。
一定要 ，we have to include the zero term if this segment have to make sense. Okay, if this segment have to make sense, right? We have to include the zero square because otherwise how you write 2 as a sum of 4 non-zero integer? It's impossible, huh? Correct or not? Yeah, it's impossible, right? It's impossible if you don't include the zero possibilities. Correct or not? It's impossible. Okay, so we have to include the zero possibility. So let's say if we really want to test you, okay, write as a sum of all non-zero integers. I think we have to. Otherwise, we have to accept the maybe easier or maybe more trivial solution. Yeah. Okay.
Yeah, okay.
Yeah. We have to include the zero square. Otherwise, doesn't make sense for what we're gonna do later. Okay, so you see how we also have this very similar theorem here. If P is an odd prime, then there exists an integer k less than P such that multiple of P will be written as a sum of 4 squared. Okay, very similar. But this proof is a little longer, not very hard, but a little longer. Okay, but so we're not going to prove to you. Okay, I put inside the note. But what you're gonna see here is there's a lot of parallel treatment in this class, right? And there's a lot of parallel treatment. So just now we proved sum theorem for sum of 2 squared. Now we also prove sum theorem for sum of 4 squared. It's very similar. We proved that multiple of P can be written as a sum of 4 squared. Just now we say that multiple of P can be written as a sum of 2 squared. But a bit different condition, you need to be careful. Okay, so from there, we can prove this. Okay, what's this? So we can show that this equation here has a solution. So whenever P is prime, we can do this. Okay, we prove for all prime. Okay, for all prime, we can split as a sum of 4 square. And then from here, we can prove it for all positive integers. Hey, you know why? If I can prove for prime, I can prove for all. Why? This one you should know. Prime factorization. Because you can write your positive integer as prime factorization, and then you use this very hard to memorize formula to write as a sum of 4 squared. Yeah. Okay. So prime is very special, you see. So this is the special property or character for prime. Okay. So in that case, if you know that, how about do this? You write this as a sum of 4 squared. So what's the first thing you should do based on the theorem that you know already? I mean, first thing you can guess. I mean, you want to try and error, you could. But then if you don't try and error, what's the algorithm? You should split them into prime first. Okay. But then I think in this case, it's easier to just look at this. Yeah. If you want to split into very prime, also can. All the primes you try also can. Then you need to combine. But then I think this is enough. 30 times 63. If you're really gonna split into primes, I think quite a lot here. Quite a lot of prime here. Let me try. 3 times 2. Wait. 3 times 2. 5. And this one is 3 times 21. So it's 3 times 7. So you got 2 times 3 square, 3 cube times 5 times 7. Yeah, you need to combine like few times. Yeah, you could try actually. I suggest you try. Then you will know the hard work.
What? What do you mean?
Yeah, because if you know the hardware, then you know what's the machinery inside this number here. Okay, so let's say if you split into 30 and 63 only, then you will just need to deal with 4 square plus 3 square plus 2 square plus 1 square, and then 7 square plus 3 square plus 2 square plus 1 square. Okay, I don't have the answer for this. You should continue. Yeah. Yeah.
这个是不是一次试出来了？不，算是吧，算是这个，不一定吃得出来，不一定，真的啦，不一定吃得出来。I mean 吃得出来 ，OK， sorry， I should take back my word， 一定吃得出来 ，why？ No. Because theorem says every positive integer can be written as a sum of both. Yeah. 那万一还有啊？就领各种计算了，有些人怎么去到？那我为什么不直接就是0.0的距离3对什么？我3变成52。
Let me see. What do you mean? So you want to write your 30 as what? What do you mean? 5 square. 5 for 25. Oh, okay, yeah, sure. Okay, yeah. I think you could. I think you could. You could, right?
You could. Then you use the formula, combine the 8. I can see whether they get to the same. I don't think they get to the same thing. Yeah, I think they get to a different combination. You could. But the point here is I split out into some integer that's easier for me to find the sum of all squares. Depend on what easy means to you. Maybe the easiest one will be this one. So I mean like this one should be like 1 plus 1 plus 0 plus 0. And then this one should be 1 plus 1 plus 1 plus 1 plus 0. Yeah, then if you look at the formula itself, right, there are like multiple 0 inside there, so there's a lot of term already disappeared inside that formula. Can you imagine? Yeah. Okay, so you reduce terms inside the formula already. Yeah. Okay. Yeah. So maybe if you have too many 0, I mean like if each of these sum of 4 square, you have 0 inside there, meaning at the end of the product, it could also appear as plus 0. So meaning what? Meaning you write it as a sum of 2 square, or you write it as a sum of 3 square. I mean, sum of 2 non-zero integer square, or sum of 3 non-zero integer square. Yeah. But I think I will try and ask my colleague whether when they say sum of 4 square, they want you to do non-zero, or is it possible to write less than 4? Yeah, or fewer non-zero square. Yeah, I'll try and clarify that. Let you know again. Okay. So can 7 be written as a sum of 3 square? This one we addressed just now, right? Okay. So next theorem. Okay, so this is about 3 square. So okay, the next part is about 3 square. So I told you that not every integer can be written as 3 square, right? But then if it is can be written as 3 square, what happened? It turns out that there is a necessary condition that when n can be written as a sum of 3 square, that is when n is not 7. Okay,
if you can read it as a sum of 3 squared, then you cannot be 7 mod 8. Okay, so this is a bit similar statement as when n can be written as a sum of 2 squared. Okay, can you imagine how to prove this? Can you imagine? Yeah, can you imagine? So when people say sum of 3 squared, right, you should like write it down like x squared plus y squared plus z squared like that. Fair enough? Yeah. But then you consider your terms just up to mod 8, right? So there are 8 possibilities you can put inside your xyz. Okay? Yeah. But then if there are 8 possibilities, then you need to talk about the possibility of their square, because I care about sum of square. Okay, so what are the sum of so square here means what? Your previous chapter, what's x squared doing? You're asking what question here? What are the quadratic residue? Okay, the possible sum of quadratic residue here. Okay, so what are the possibility here? So you only get how many of them? I think we counted before, right? Oh, but this is not prime, so the formula doesn't apply. Okay, it doesn't matter. So if it is prime, it should be p minus 1 over 2, right? The number of different quadratic residue. But this is not a prime, so formula doesn't apply. Okay, so we just compute it. So you get 0, 1, 4, 1, 0, 1, 4, 1. Okay, so you really just get 0, 1, 4. So how many possibility you can get here? How many possibility you can get here? 0, 1, 4. How do you add up? So either you get 1, 1, 1, 1, 4, 4. Oh, sorry, 1, 1, 4 first, or 1, 4, 4, or 4, 4, 4. Correct? Okay, so these are the all possibility you can get. Okay. Should we include a zero case? I think we should include a zero case. So let's include the zero case as well. Wow, there's a lot of. Let me see. Should we include a zero case? I think we should, huh? Okay, if we're gonna, yeah, okay. Let's include a zero case. So zero case will be, wow. So 3 times 3 times 3, how many possibilities? 51. Oh. Wait, let me think. But we don't care about the permutation, right? So can reduce a bit, huh? 27, huh? Huh? How you calculate that? 9 times 3. Why 9 times 3? Wait, how to calculate all the possibilities without considering the permutation? Divide by 3 factorial, is it? I think divide by 3 factorial. So 3 times 3 times 3 divide by 3 factorial. Is it 6? We don't care about permutation, right? We just care about so this one got already. And then what else? What's the combination? 0, 1, 4? 1, 0, 0? No lah, 1, 0, 0, 0, 0, 1 we consider as one type. Yeah, we don't care about permutation. What else? 1, 1, 4? 1, 1, 4 got already. Yeah, I think that's all right. Huh? Did I include all the possibilities without permutation? Already. What's how to calculate the total number? I think this is a high school problem. Every spot I got 3 choice, right? So 3 times 3 times 3, right? Total is 27, but I don't care about permutation. So how should I compute? How many possibilities? Huh? 忘了，忘了，谁记得？ Without permutation. Okay, I think it's enough. Okay, so can you sum all of these? What do you get? All these possibilities, what you get? For all these possibilities, what's the sum you can get? Okay, so if you sum all these, okay, so 0, 1, 2, 4, 16, 16 mod 8, 0, 3, 6, 8, 9, 9, 1, 12. So this is 4, 0, 1, 4. Okay, so you can get 0, 1, 2, 3, 4, 5, 6, but not 7. Okay. Okay. Yeah, is it good? Okay, you don't get 7 or 8. You only get 0, 1, 2, 3, 4, 5, 6. No 7. Okay. 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 All right. So next, so this give a equivalence condition when you can write as a sum of 3 squared if it is not a form of 4k times m and m is 7 mod 8. So you cannot have a single 7 mod 8 appears as your factors. And also some power form. Forward directions is easier, backward is hard. Okay, backward is hard. Even your textbook don't present it. So meaning, if it's not a form of this, why can you write as a sum? Or if you cannot write a sum, why it has to look like this? Okay, this part is and the backward is hard. So maybe I write here. So this direction is hard. Okay, forward still okay. Put it in the note. Backward. So backward means if it's not in this form, why can you write sum of 3 squared? Or in other words, if it cannot write as a sum of 3 squared, why must it be written as this form? Because this is hard. No proof. I don't include the proof. Okay, so how about we stop here? We stop here. Okay, let's stop here. Okay, so see you on tomorrow and then also on Friday. Yeah. Okay, tomorrow we will discuss assignment and also do some exercise from tutorial. Tomorrow, yeah. And then Friday, I think no. And Friday maybe because it's the last class, we could take photos on Fridays. Yeah. That was okay. See you tomorrow. Hey.
就是我自己疏忽弄了一道题。
哦，对。